Okay folks, I'm going to run through some of these mechanical wave practice problems and give you some guidance. Most of y'all are finding these pretty straightforward, but there's one or two where either your understanding of the vocabulary is not up to snuff, you haven't learned all the vocabulary, or you're just not thinking carefully enough. So you're going to see me draw a lot of diagrams here, which I always recommend, and that's going to help me and you think more carefully about some of these. So number one, pretty straightforward. We've got a clock, and this thing is vibrating, and that's going to create sound, and that sound is going to travel a certain distance until it is heard. Now, in order to be heard, it has to go into someone's ear. Okay, so there is an ear somewhere 515 meters away. So that distance is 515 meters. If there wasn't an ear there, the sound wouldn't be heard. Hearing sound is something your brain does to wave pulses. That old saying, if a tree falls in a forest and there's no one around to hear it, does it make a sound? No, it doesn't make a sound, because sound is something your brain does when longitudinal compression waves into your ear. It's a way. Sound is how your brain interprets those waves. So, long story short, it has to enter someone's ear in order to be heard, and it takes. The ear is 515 meters away, and it takes 1.5 seconds for them to hear it. So we can calculate the velocity. We don't have frequency or wavelength, so we can't use this equation. We have to use distance over time. So that'll be 515 meters over 1.5 seconds. That's going to give us the speed of sound at room temperature, 343 meters per second. Now, some of us are getting distance confused with wavelength. Distance is that red line, the distance that the wave moves through air. The wavelength is the distance between these two compressions. So the wavelength would be the distance here, or you can measure the wavelength here. That's the wavelength. That's the distance between each of those wave pulses. And we'll calculate that in a second. But it's different than distance, so don't get those two mixed up. Now they give us the frequency of this wave, and they want to know the period. Period is simply 1 over the frequency. Frequency tells us how many of these pulses are sent out each second, and period tells us the time in between from one pulse to another. So how long does it take between the first and second pulse, the second and third pulse, and so on. So 436 pulses are sent every second. How many seconds does it take to send one pulse? 1 over 436 will give us that, and it's going to be about 0.00229 seconds, or 2.29 milliseconds. Both of those answers are equally valid. So that's how long it takes to generate one pulse, or that's the time in between pulses. Now we can get the wavelength. We know the velocity from part A, 343 meters per second, and we know the frequency because it was given in part B, 463 hertz. So the velocity, or the wavelength rather, the symbol for wavelength is lambda. Remember, it's the Greek symbol lambda. So we use our wave speed equation. Velocity equals frequency times wavelength. We need to divide each side by frequency. Cancels on the right. And we divide on the left as well. And we're going to get that the wavelength equals velocity over frequency. So 343 over 463 is going to give us 0.787 meters. And now that is the distance between each of these wave pulses, 0.787 meters. So notice the difference there between wavelength and distance. Wavelength is the distance between each pulse, and distance is how far the energy travels through the medium. Okay? Remember, a wave is just the transfer of energy through a medium. Okay, so there's our wavelength for part C. In number 2, we have to understand how sound reflects. An echo is essentially a reflection of sound. That's what we call a reflection of a sound wave. We call it an echo. When you hear an echo, sound goes out of your mouth and it's going to hit some object. Usually it's kind of a stiff object, like a cliff made of rock or something. And the hiker shouts. The sound travels to the cliff. This is the cliff here. It's just a vertical wall as I've drawn it. And it's going to travel 465 meters to that cliff. Now the person hasn't heard his echo yet. He may have heard himself when he first shouted, but he hasn't heard his echo yet. An echo is when you hear that sound twice. And the reason you hear that sound twice is because it's going to hit some object like a cliff, and then it's going to reflect or change direction. And then those wave pulses come back, all the way back to the hiker, into the hiker's ear hole. And then they have heard the sound a second time. In other words, they've heard that echo, that reflective sound. So it travels another 465 meters to get back to the person. So the key idea here is in order for it to be an echo, it goes to the cliff and comes back. So the total distance here is what most people are getting wrong. The total distance it travels is not 465 meters. The total distance is 2 times 465 meters, or 930 meters. Okay, and that's because it must go to the cliff and then return back to the hiker's ear before he hears it. Remember, sound is not heard unless it goes in someone's ear. It's not sound until it's heard by someone's brain. So, the amount of time it took for the wave to do that is 2.75 seconds. So we know the total distance the wave traveled, and we know the time it took to travel that distance. We can calculate the velocity using distance over time. That's going to be 930 over 2.75, which gives us 338 meters per second. And you can also tell that it's kind of a chilly day. The speed of sound is kind of slow, so it's kind of a chilly day out there wherever he's hiking. All right. Now in B, we are given the wavelength, 0.75 meters, and we already know the speed from part A. So we can calculate the frequency of this person's voice. And this is going to kind of tell us how high or low pitched the person's voice is. So velocity equals frequency times wavelength. That's the equation that'll work for us. We're going to divide each side by wavelength to isolate the frequency variable. So velocity over lambda equals frequency. 338 over 0.75. That's going to give us, let's see, I don't know where I'm getting these numbers. 338 over 0.75, and that's going to give us 451 hertz. So that's the frequency of that person's voice. It's about close to an A note. Their voice is close to an A note. And now we can get the period. We know the frequency is 451 hertz now, and the period is just 1 over the frequency. So 1 over 451 hertz gives us a period of 0.0222 seconds, or 2.22 milliseconds. Both of those answers are equally valid. So that's number 2. All right. Here's number 3. Most people didn't have trouble on this, but I'm going to do it anyway. They want to know the speed of a periodic wave that has that frequency and that wavelength. So we use the wave speed equation. Velocity equals frequency over wavelength. No algebra required. The frequency is 3.5 and the wavelength is 0.7. That's going to give you a velocity of 2.45 meters per second. In number 4, I'm giving you the velocity of a wave and its frequency, so we have to find the wavelength. So we use our wave speed equation, velocity equals frequency times wavelength. Isolate for our unknown, so divide by the frequency, and we get that velocity divided by frequency equals wavelength. So that's going to be 15 divided by 6. So we're going to get a wavelength of about 2.5 meters. In number 5, we say that 5 pulses are generated every second in a tank of water. So they're generating pulses. They're making these wave pulses in a tank of water every 1/10 of a second. And they're making 5 of them every 1/10 of a second. And they want to know what the speed of the wave is if the wavelength is 1.2 centimeters. So when they're telling you the number of pulses and how much time those pulses are made in, they're telling you how to calculate the frequency. The number of pulses, or number of oscillations, is 5, and the time it takes for those 5 oscillations to happen, or those 5 pulses to be created, is 1/10 of a second. So that's how we calculate frequency. The number of pulses, or the number of oscillations, or the number of vibrations over time. So here we have 5 pulses in 0.1 seconds. So that's going to give us 50 hertz. 50 pulses are sent for 1 second. Now, I bet that person's really tired if they're making those pulses by hand. Now we can get the velocity though, because we already know the wavelength. The wavelength was given to us, 1.20 meters, and we can get the velocity with that frequency and that wavelength. The velocity will be frequency times wavelength. 50 times 1.2. The velocity comes out to, let me just make sure my calculation's correct here. 50 times 1.2 is 60, but this should have been 1.20 centimeters. It was given to us in centimeters, so I need to convert that to 0.0120 meters and change that 0.0120, and it actually gives us 0.6 meters per second. There we go. Got to be careful with those unit conversions. I almost missed that. But the unit for that wavelength is centimeters, so I had to convert that to meters before I calculated my velocity, and it should come out to 0.6 meters per second. Moving on to number 6, we've got a periodic longitudinal wave, so that's like a sound wave, has a frequency of 20 hertz and travels along a coil spring. If the distance between compressions is 0.6, what is the speed of the wave? Now, the distance between compressions, that is the definition of wavelength. The distance between 2 compressions. So I'm telling you the wavelength there. It's 0.6 meters. And I've given you the frequency as well, 20 hertz, and just want to know what that wave speed is. Okay, so that distance between compressions is the definition of wavelength. And I expect you to know the definitions of things. Know the vocab, know the definitions, and know how to interpret them from a word problem. So velocity will be 20 times 0.6. I do believe that is 12 meters per second. So that particular wave is traveling 12 meters per second through that spring, which serves as the medium. Okay, now we get into these 7 and 8, which deal with interference and superposition. So the diagram, I'm going to draw a diagram first before I even start solving the problem. So what we have here is a string. Now let's consider a string that's fixed at two ends. So it's anchored there somehow, and down here it's anchored somehow. And now the string, before we pluck the string to send waves pulses through it, the string is in equilibrium. All the points on this string are at a position of 0 from the equilibrium because they're on the equilibrium line. When we send a wave pulse through, it causes a pulse to be created, which will either be going above or below the equilibrium. And we're sending two pulses through this string. One pulse we're sending to the right with an amplitude of 0.5 meters above the equilibrium. So that pulse is above the equilibrium, and the amplitude of that pulse is positive 0.5 meters. But we're also sending another wave, a slightly smaller wave, to the left through that string. So that wave goes to the right, and this wave goes to the left, and it has an amplitude of positive 0.3 meters. Okay, so there is the problem. These two waves are moving towards each other, and when they meet, they will interfere. So first thing is, what's the polarity of the wave pulse moving to the right? Well, the polarity is positive. That's the polarity. Why? Because it's above the equilibrium. And the equilibrium is just the string before we send a wave through it. The equilibrium is just that flat string. So the particles have been pushed above the equilibrium. Now, we need to know if the wave pulses will constructively or destructively interfere. And for that, we only need to look at their polarities. They both have a positive polarity, so they will constructively interfere. They are both above the equilibrium, or in other words, they have the same polarity, so they will constructively interfere. And the reason for that is because they have the same polarity. In this case, they both have a positive polarity. But if they both had a negative polarity, they would still constructively interfere. And now it wants us to calculate the superposition of the two wave pulses. So the superposition is the combined amplitude. A stands for amplitude. So the combined amplitudes, we just add the amplitudes together. And it was positive 0.5 plus positive 0.3. So the superposition, when these two waves interfere, will be 0.7 meters. So when they interfere in that string, they're going to make a pulse that's even higher. If that is a height of 0.5 meters, this would be even higher, 0.7 meters, when they interfered with one another. Okay, so that would be the combined amplitude as they pass through or interfere with one another. The string would go up to 0.7 meters. That pulse would go up to 0.7 meters above the equilibrium. And now in number 8 is kind of a counter example to number 7. So I still have a string, and let's just say it's fixed at both ends, and right now it's in its equilibrium position. So the amplitude everywhere is 0. But we're going to pluck the string at both ends to send a wave pulse through it. Now, on the left, we send one to the right that is 0.7 below the equilibrium this time. So the amplitude of this wave, A1, is negative 0.7 meters. And we're going to send another wave to the left. So this wave, V1, is moving to the right. And then we send another wave to the left above the equilibrium, negative or positive 0.3 meters, because it's above the equilibrium, and this pulse is moving to the left. So the polarity of the wave pulse moving to the right, A1, the polarity is negative. Why? Because it's below equilibrium. Okay? And we want to also know how they will interfere. They will destructively interfere because they have opposite polarity. Okay, the wave pulse moving to the right, A1, has a negative polarity because it's below the equilibrium, and the wave pulse moving to the left, A2, has a positive polarity. So the polarities are opposite, and that means they will destructively interfere. And now it simply wants us to calculate the superposition, which is just the sum of the amplitudes. So the combined amplitude when they interfere, otherwise known as superposition, is going to just be equal to A1 plus A2. But A1 is negative 0.7 meters this time, so be careful with that. A2 is still 0.3 meters, so we're going to get a negative 0.4 meters for our combined amplitude, for our superposition. So that means on our string, when those pulses combine, it's going to have a negative amplitude, a negative polarity that is 0.4 meters below the equilibrium when they interfere and pass through one another. Okay, I hope this has helped us make a little bit more sense. Watch it again, and if you still have questions, shoot them to me in my inbox. Thanks for watching.